Today we are going to touch upon a very important problem on authentication and authorization for MCP servers, and we are going to dive into the mechanisms and issues involved. Since Anthropic launched MCP in November 2024, there has been a lot of work around MCP security, and this has become especially important with the rise of remote MCP servers. In this session, we'll start by understanding what does Auth really mean, and we'll introduce OAuth 2.1. Then we will dive into how OAuth applies within the MCP context and take a deeper look into specific RFCs like dynamic client registration, protected resource metadata, authorization server metadata discovery, and so on. And then we will discuss why MCP Auth is hard with the challenges and the issues involved and what work is being done to actually counter this. Finally, you will take a sneak peek into how TrueFoundry is leading the way in MCP security within its MCP gateway offering. So let's get started. First, let's understand what is MCP authentication and authorization. So authentication is where the MCP server verifies the identity of the MCP client. Is it who it says it is? And authorization is where the server determines if that authenticated client has the necessary permissions or not to access the requested resources. Now, why is this actually needed? Think about authentication. Without that, attackers can impersonate users and leave no trace. Think about what if the token in a header-based authentication is leaked. There will not be any trace of the user doing any activity. And without scoped authorization, think about an overprivileged chatbot which can actually cause irreversible damage if it does not have limited scope. Right? Now, in the context of MCP, why is this really important is also because accessing personal data is very common, right? So unlike weather APIs, which are public MCP servers, a lot of the MCP servers revolve around personal data, like think about Gmail, Slack, GitHub, right? You need to have some authorization and authentication in place. The second thing is, earlier what used to happen is that MCP clients could directly talk to MCP servers because they were talking through standard IO transport, and the authentication there was minimal. As the MCP ecosystem evolved, the need arose to call MCP servers across the network with the streamable HTTP protocol. And this is why authorization and authentication really becomes important. Now, when we're talking about MCP and the entire flow, the MCP client is actually sending a request to the MCP resource server, and it is governed by the MCP authorization server, which is very well defined. But what happens is sometimes the MCP resource server needs to access additional things from a non-MCP resource server, right? And there is a non-MCP authorization which is basically governing that. This can be HTML, SAML, SOAP, XML, right? And these are all different ways in which the authentication and the auth can actually be done. So what we're going to discuss is this very well-defined and important first hop here, and I will talk about the second hop towards the end, what challenges this poses. The first thing that comes to your mind when you think about authentication and authorization is typically, can we use a password or an API key to access a remote MCP server or not? But there will be certain issues if you're actually doing that. If the client app is actually relying on a password to do that. How can the MCP server instantly and granularly revoke this client's access? Would it trust the client to securely store the password or the long-lived API key which can allow access to the MCP server resources? Can the MCP client only access very specific MCP resources, or does it have, blanket access to everything? Did the user explicitly agree to give this specific client limited access to their MCP account? So we need something more elegant in order to counter these issues. Let me introduce OAuth now, which is open authorization, and this is an industry standard framework that allows a user to grant a third-party client limited, revocable access to resources on an MCP server without sharing their primary credentials. So you're not sharing your primary credentials, and this is basically the field of delegated authorization. Now, why this is also important and why OAuth actually took off is that modern organizations have existing IDPs or identity providers or even OAuth 2 authorization servers, which is really built around OAuth. And the maintainers of MCP chose to piggyback on OAuth 2.1 rather than creating something from scratch. So that's why OAuth has actually been adapted to MCP a lot. This means that an MCP server can trust tokens which are issued via the OAuth flow, and MCP clients can actually obtain those tokens by redirecting users to an authorization server which is using OAuth under the hood. And we'll talk a lot about this flow in a lot of detail. But first, let's understand what components are involved in OAuth. You need an authorization server, you need an access token, and you also have a protected resource, which is an MCP server API. And I'll take an analogy of a hotel check-in here. The authorization server is the front desk person. The access token is kind of the room key that they issue, and the protected resource is obviously the room itself. So what the authorization server is doing is it's not giving you the master key. The person at the front desk is not giving you a very permanent key or even a master key that can open, the same room or all the rooms. So you have a limited scope. You can only open one room. And the second thing is that access token can expire, or that room key expires when you check out. So think about this. The key card is temporary, it is revocable, and it only opens your room. It has limited scope. And this is exactly what OAuth also enables. So when the user actually authenticates with the authorization server issues an access token. And that access token can actually unlock the limited scope, which is the specific resource that it is authorized to unlock. Now let's see how this solves our static credential, which is the password API key problem. The first thing is obviously you are using revocable access tokens. So the first issue is automatically solved. The second thing is there is no absolute credential or static credential sharing. It is delegated authorization. So the client never sees the permanent password, so to speak. The tokens enforce limited scope, granting only specific finite permissions. And finally, the user has to give an explicit consent via a screen which details all the requested permissions. And we'll talk about the flow in more detail. Now, in an enterprise context, the enterprise admin typically expects all of their applications to be put under a single sign-on system, which is an SSO. And an AI agent which is using MCP is just another application for enterprises that they want to be able to integrate into SSO. This is why we need authentication and authorization, and authorization for accessing MCP servers is enabled using OAuth 2.1, which is an industry standard, and authentication on the other hand is basically identifying the user, and that is enabled using two methods. The first one is OIDC, which is OpenID Connect, which is built on top of OAuth 2, and it uses ID tokens, which are basically JSON web tokens. And the second method is SAML, which works via SAML-based XML assertions, right? So either of these two authentication methods can actually work within your entire flow. Now, let's dive into some advanced OAuth mechanisms for MCP. So how does OAuth actually translate to MCP? And here I will talk about the MCP authorization spec, which basically details out what all is needed. And the first version came out at the time of MCP launch in November 2024. The second version came in March 25 that we are going to talk about, and the third one in June 25. And March 25 was really a very important update because official support for remote MCP servers came, where legacy HTTP plus server sent events, or SSE, was replaced by the streamable HTTP protocol. And this spec defined how the MCP server behaves and how a user needs to interact with it to log in. And I'm talking about remote MCP servers mainly. Remember that if you're doing local MCP servers and you're doing MCP locally, you do not need a very large amount of authentication and authorization. So a lot of the work is being done around remote MCP servers. And in March 2025, all the OAuth 2.1 best practices were actually followed, which was a very nice update. However, there was one issue, and we're going to talk about that issue here. The issue was that the MCP client was sending authorization requests and resource requests to the same MCP server, which basically had the authorization server and the resource server both. So you can see in this diagram that the authorization endpoint and the API or the resource API endpoint are both contained within the MCP server. So as a MCP server developer, right, you would need understanding of how to develop an OAuth authorization server, which is very limiting. So in the June 2025 version update, what happened is that they decoupled this and separated this, where the MCP authorization server was kept separate, right, which is a simple OAuth server and a lot of practices around that. And the MCP resource server is all you need to develop as the developer of an MCP server. So now let's deep dive into the authorization flow. So a user comes in, they start the login action, and the redirection is done via the MCP client to the OAuth server. The OAuth server basically shows the consent screen to the user, and the user then authenticates themselves and gives their consent. This can be via regular password login, two-factor authentication, either using IDPs on the enterprise side or the consumer side. And then the redirection is done to the MCP client with the authorization code that is returned by the OAuth server. Now with this authorization code, what happens is that the MCP client now sends a request for a token. So the MCP client gives the authorization code, their client ID, and the client secret to the OAuth server, and they get a token response. And with that bearer access token, they send the MCP request to the server and get back the MCP resource response from the MCP server. Now, if you look at all of this, you can see that only in the last two steps, the MCP server is actually doing certain activities, whereas the MCP client is pretty much involved across the entire flow. And I have demarcated two specific areas. One is the front channel and the back channel. In the front channel, the whole redirect process is occurring with the user being in the browser, logging in, redirecting to the IDP for authorization, and so on. And in the back channel is where the actual token exchange is occurring, basically. One more thing that you need to keep in mind is that as an MCP server developer, all you need to know is how do you validate that access token. So what does your OAuth server really say about how should you be validating the tokens? And that's all you need to do in the last two steps. Now, there is a challenge in terms of how this all used to be done before certain standardizations were done. So earlier, most OAuth clients were hard-coded with the configuration details of the authorization server. That is the URL that they need to hit for requesting an authorization code, the URL for requesting a token, and even the authorization server location or the API that they need to talk to. And the client basically needed a bunch of data to be correctly configured in order for this entire flow to work. Now, one of the RFCs, which is the protected resource metadata, was actually launched in April 2025, which dealt with one part of this. That is, how do you configure an MCP client with only the single URL of the MCP server, which tells it the location of the authorization server, right? And this is also a requirement as part of the MCP authorization spec. Now, if you think about the protected resource, what is that? That is the MCP server API, which is getting protected by the OAuth server, right? So this protected resource metadata, we'll see it in the flow. What it does is it is built on a well-known endpoint. So once the client is trying to access without the necessary authentications in place, it basically redirects to this well-known endpoint where it gets the location of which OAuth server is actually protecting that resource, right, which is the MCP server. And once it gets the location of that authorization server, it basically can hit that and get the necessary information and basically start the OAuth flow, right? So what is that necessary information that the MCP client actually gets? That is governed by the authorization server metadata RFC. Right? So MCP client can get all the necessary OAuth endpoint URLs like authorization, token, revoke, etc. via a single standard JSON file, right? And this is basically under the purview of authorization server metadata RFC. And this is required as part of the MCP Auth spec again. And this is being published by the MCP Auth server. Now let's go over the sequence of how this all actually happens. So the client first attempts an unauthenticated MCP request. So let me zoom in a bit. And that basically gives an HTTP 401 unauthorized error. Then the protected resource metadata flow is triggered. The first thing is if the header includes the resource metadata, then basically that authorization server URL is returned. Otherwise, there is a fallback option where well-known URI probing is done, and then finally the authorization server URL is returned. If you want to know more, you can read the official MCP authorization spec. Now, once this URL is retrieved, the authorization server metadata URL is actually built, and you get information from that endpoint. You get the authorization server metadata, and with all of this in place, the MCP client has all the information to then start the OAuth 2.1 authorization flow. So obviously that occurs, then the token exchange happens, and then finally the MCP server is hit with the request for returning the resource. So the first part of this is the protected resource metadata, and the second part of this is the authorization server metadata. Now let's switch gears and talk about dynamic client registration. With dynamic client registration, the request is to enable connection to MCP servers without any pre-registration. So earlier what used to happen is that client developer registers for credentials at the OAuth provider beforehand, and they manually log in into an admin panel, create a new client application and get a client ID and secret. Or enterprise admins basically add client credentials into their IDPs for internal applications. And there is a lot of admin overhead and key management manually that occurs here. Now, how do we do this without any manual steps involved? What dynamic client registration does is it lets an MCP client automatically register itself and instantly receive a client ID and secret, right? So it basically sends the OAuth server at runtime a JSON request, and the OAuth server instantly validates it and issues that client ID and secret, and the authorization flow starts. Now, one thing to note is there is no authentication of that client registration request. Right? And this raises a few issues which we'll talk about shortly, but overall this is a very nice thing to do. And this is not a requirement, this is a recommendation as part of the spec. If dynamic client registration is not there, the spec mandates that either the client ID and secret is hard-coded via some manner, it is provided, or a UI pops up where the user is prompted to enter that information. Now let's revisit our sequence diagram. So this is what we just saw with the protected resource metadata flow and the authorization server metadata flow. But I just want to expand the OAuth authorization flow here. And this is what we are going to look into. This is where you have all of the authorization server metadata. And what happens here is that the client registration occurs dynamically. So the client registers with the callback URL. The authorization server then gives it back a client ID and secret, and that is stored in a database, right, along with the callback URL. The callback URL is very important, which is used later. The client then sends the authorized request with these details, and the authorization server basically responds with the authorization code on the same callback URL. And after that, the token exchange happens as per the regular flow, right, which is what we see here. So this is where dynamic client registration is actually occurring, right? Which is as part of the OAuth 2.1 authorization flow at runtime. There are a few other RFCs, and I'll just cover one more, which is resource indicators for OAuth 2.0. This is for precise token audience restriction, where the access token is cryptographically bound to the specific MCP server's URL. So there can be no other malicious MCP server sitting in between the MCP client and authentic MCP server, right? So there can be no attack as such, and this is what this RFC actually enables, and it prevents the misuse against other enterprise APIs as well. So this is the principle of least privilege that is getting followed. And finally, to just wrap up the discussion around RFCs, a lot of these are there, a lot of these are being developed, and this is what makes MCP Auth really, really hard. Now let's go into specific challenges and developments that are occurring. As we discussed, because there is no pre-registration and authentication of the client registration request, there are security pitfalls in DCR. The first thing is you can have a bad client which can ask to be registered, and there can be security issues because of that. The second thing can be you have a bad server, and the server basically has a bad URL that is selected and inputted into a chat client, and that can do any number of things. Or you can also have one more combination, which is man in the middle, where you have authentic MCP client and MCP server, but there is something in the middle which is malicious, either an MCP server or a client, which is causing issues in security. Now, the workaround here is basically, if you think about two of these issues, which is bad server and man in the middle, the issue is with the bad URL which is being selected and inputted into the chat client. And with an MCP registry in place, what happens is that you authenticate or you verify the URL of the server, and that is what the MCP registry enables. So these last two issues are actually solved if you're using MCP registry, and you basically can have your own registry endpoints and deploy your own registries. The official ones that is deployed yet does not have these moderation capabilities, which actually checks these issues. And the second thing which can help remember is what we talked about, resource indicators, where the access token is cryptographically bound to the MCP server, the specific MCP server. So this man in the middle attack can be avoided using that. Now, in general, dynamic client registration as a technique has certain pain points, because although this is a very old RFC, when it is applied on top of MCP, it raises a certain amount of issues. Think about the first issue that occurs. Now, remember, we are writing the client ID, the client secret, and the callback URL to a database. And earlier what used to happen is that a lot of checking used to happen when normal clients used to get registered, right? Were the app standards getting met before giving the client ID and secret? Now what happens with LLM applications is one application can launch up multiple MCP clients, and if all of them are trying to get registered, a lot of data gets generated, which can easily lead to unbounded databases. So these databases are not really built for that kind of scale. That causes issues. The second thing is expiration handling. Now with this large amount of data, you have to obviously purge the older client IDs. And if you have an expired client ID, you are not able to have a redirect URI anymore. If you try to refresh a token or start a new OAuth flow, even if you want to send an error code with the callback, that leads to open redirect, which is a security risk in itself. So expiration handling is a pain point. The third thing is that because one application can have more than one and a lot of clients, if you're looking at the client screen, which shows you authorized clients, it is not really useful, right? It is a lot of noise and clutter out there. So this is really a pain point. To solve all of this, some work is going around SEP 991, which is basically client ID metadata documents, which can actually counter these issues. And I'm showing you a tweet by David at Anthropic here, who is the co-creator at MCP. And this is a tweet from 2 weeks back on 16th October, where he says that today MCP core maintainers accepted a proposal that the next version of MCP will make use of client ID metadata. They will make the use of DCR no longer necessary. So what does client ID metadata documents actually do? It basically puts the URL to the metadata file as the client ID. So the client ID is mapped to the URL of the metadata file, right? And the metadata file has all the application information, including the redirect URI and so on, right? And this enables a one-to-one mapping between an application and the client ID, right? So although there can be, n number of clients, it's basically a one-to-one mapping that occurs. Now, let's talk about MCP in the enterprise setting. Now, remember, enterprises like to keep everything under a single SSO, a single sign-on system. Now, think about a usual flow where a user is logging into an application, be it Cursor or Claude or any thing like ChatGPT and so on. That's a user app, and they are authenticated by the enterprise IDP. So they redirect to login, and an ID token is returned, which is the authentication part, right, as part of OIDC, or even a SAML based assertion is occurring, right, regardless of that. Then when the enterprise IDP sees that ID token, it authenticates the user, obviously trying to get the user's consent as part of the authorization, and redirects with the authorization code, and the user is then basically logged in. Now, if that user app, let's take the example of Cursor, if it wants to access, let's say, an MCP server Slack, it again tries to get consent from the user that, okay, do you want to authorize this application to access your Slack data? Similarly, the user gives the consent again, and the access token is returned. And then obviously the MCP resource request can occur after that. Think about one more server. If you want to also access GitHub through your user application, again, this flow has to occur, right? And you have to give consent that, okay, I want to enable this user application to access my GitHub data. Similarly for Atlassian. So the first issue that this basically poses is that it is not a really good user experience. What if you have 20 MCP servers that you wanted to connect to your application? Would you really do this 20 times the SSO flow? Obviously not. That is not a very good user experience. And the second thing is that As a user, as an employee, you are telling the user application to access data on Slack, GitHub, and Atlassian, and this should really not be your call. It should be the call of the enterprise IT admin, who in fact does not even know that you're doing this, because it is not seeing these app to app connections. It is only seeing the first time you're logging in into your user application, because the next few times it is launched by the user application itself, the requests. Enterprise IT admin does not really know what's going on under the hood. So this is basically solved by cross-app access, which is officially called identity and authorization chaining across domains. Basically, the first two steps are same. Once the ID token is returned, then you post the ID token with the cross-app access request to the enterprise IDP, and the cross-domain JSON web token is returned. Now you're logged in at this point. Now for any subsequent connections from the application to different MCP servers, all you need to do is the cross-domain JWT is basically posted by the user application, right? By, let's say, cursor in this example. The MCP server validates the JSON web token using signature with the IDP public key automatically. There is no consent screen where you need to intervene, and then the access token is returned, right? So you just need to do one click and you're done. You don't need to go through the entire SSO again. And the benefit here is that the enterprise IT admin also has visibility over what's happening through this cross-app access. Lastly, let's talk about second hop authentication, which is not governed by MCP. And one thing which is mentioned in MCP auth spec is to avoid token pass-throughs from the first hop to the second hop. Non-MCP authorization servers, for example, because this can lead to token leakage and security risks. Otherwise, this is not very well governed, like I mentioned earlier, and this is application dependent and do it yourself. So a lot of the standardization has to occur here by the community, and guidelines have to come in place. So these are a lot of challenges that we have discussed around auth for MCP, where hopefully by now you should have a sense of what is really happening in the space. And I want to introduce what we are doing at TrueFoundry in MCP security. This is a snapshot, as promised, into a webinar that we took with Palo Alto Networks, who is a leader in the cybersecurity space. They have launched Prisma Airs, which is one of the most comprehensive AI security platforms. And shortly you will learn from our CTO what are we doing in MCP security at TrueFoundry and how we are enabling the best practices as part of our MCP gateway.
TrueFoundry, like in the MCP gateway, you can integrate MCP servers with these authentication authorization mechanisms. So in the diagram that I was showing earlier, usually MCP servers will have their own authorization system. And there are three ways of authorizing it. One is your OAuth. One is header based auth. So like you pass an API key in the header and then the MCP server allows you to talk to it. And some MCP servers might have no auth. This is not recommended for production, but for dev, you can do that. So all these methods of authentication are supported on TrueFoundry. And what the gateway does is it provides you a three-layer authorization and authentication system. What I mean by that is a developer talks to the gateway. So this is the MCP server that the developer wants to access or the agent wants to access. So what they do is they send us your own IDP token. So you can send us your Okta token or the TrueFoundry token. The gateway will first verify that you are the person that is trying to talk to the gateway and you belong to the organization. So the first step is that. The second step it does is it checks that you actually have access to talk to the MCP server. So only if the infra team or the platform team has given you access to the MCP server, then only you will be able to allow to talk. Otherwise, the gateway will say that you don't have a permission to talk to it. And the third thing is like it will translate your TrueFoundry token to the Slack MCP token or the GitHub token, whichever token is expected by this MCP server. So the translation of the token is also handled by the gateway. So it can translate that one single token of yours to like hundreds of different tokens that are expected by each of these MCP servers. So that is also handled by the gateway. So this is why we call it the three-layer authorization system. And this kind of builds out a very solid foundation within the company that gives you a very long-term security and governance that you can control who in the company can do what. There are few use cases for this using of authentication and authorization. One is your developers trying to access the MCP servers within your organization. The second use case that is also coming up now is how do you enable your end customers to access your own internal MCP servers? So in that case, the concept is the same, like you want your end customer to be able to access X, Y, and Z and not the other MCP servers. So even that is a use case that is coming up, and that also the gateway can do without you having to build any other layer in front of the gateway. So that is one more thing. Regarding tool level authorization, what TrueFoundry does is it basically, we have a concept of a virtual MCP server. So you can actually combine tools from different MCP servers and a set of tools. So you can say that I need 2 tools from Slack, 3 tools from GitHub, and maybe 4 tools from Atlassian. And I will create a virtual MCP server. So you're not writing a new MCP server, you're just creating a virtual entity and you're giving it access to your agent. So then your agent thinks that there is only one MCP server which has access to this few set of tools. And this allows you to do like very fine-grained authorization on a per tool level across MCP servers. So this is something that is really, really important and gives a lot of flexibility to developers and agents.
Thank you for watching.